Welcome. We are now considering residual properties. As we said earlier, residual property is nothing but the difference between the actual quantity and the ideal gas quantity. The advantage in using residual properties is that you can get generalized correlations, and generalized correlations can be used in general maybe for most gases, and we do not have to worry about looking at particular properties for particular gases. In the last class we were somewhere here, we were in the middle of developing generalized correlations for residual properties, and we said from the definitions of the residual properties we could write the actual pressure as the product of critical and residual pressures, and therefore the differentials. For example, the differential dP can be written as Pc constant times dPr. Similar things could be done for the temperature, and if we substitute these values in the three equations that we had developed for the thermodynamic properties in terms of for the thermodynamic properties such as Gr by RT, Hr by RT and Sr by RT, we had developed these expressions in terms of the easier to measure compressibility factor, pressure and so on, and temperature. So we said that if we could substitute the values in terms of the residual properties, we could get generalized correlations in terms of residual properties, and the usage of them would become a lot simpler in terms of need for data. And towards the end of the class I had said if you can substitute these expressions into equations 336, 337 and 339 and develop the correlations, it will be better, you would understand where it comes from. For example, to give you an idea, if you had not already done, for T here you put in Tc Tr, for P here you rather dP here you could put Pc dPr, and P would be Pc Pr, and the Pc Pc would cancel out here, and when you are integrating with respect to the variable Pr or the reduced pressure, it makes sense to have the limits of integration in terms of the reduced pressure. Therefore, these would automatically change and we could get expressions in terms of the reduced properties. Hopefully you would have gotten expressions such as this: Gr by R Tc Tr, when we substituted T in terms of Tc and Tr, equals integral from Pr reference to Pr2 of Z minus 1 dPr by Pr. Pc will cancel out here, and so we would get this. We will call this equation 347, and similar substitutions would yield us Hr by Rtc equals minus Tr squared integral Pr reference to Pr2 dou Tr of Z at constant Pr dPr by Pr. We will call this equation 348, and Sr by R would turn out to be minus Tr integral of Pr reference to Pr2 dou Z dou Tr at constant Pr dPr by Pr minus integral from Pr reference to Pr2 Z minus 1 by Pr dPr. Therefore, we have all these in terms of the reduced properties, and since the reduced properties are applicable over a large variety of gases, you could apply these equations without the need for particular data for particular gases. Let us move forward, and before that it is good to note that as earlier, the lower limit for integration, the Pr reference, is usually taken to be 0. We could choose that as anything, it is usually taken to be 0, so that we do not have to worry about values there. Now these equations 348 and 349 which are here, HR by RTC equals minus TR squared integral of dou Z by dou Z dou TR dPr PR, and SR by R equals minus TR integral PR reference to PR2 dou Z dou TR at constant PR dPr by PR minus of integral P reference to PR2 Z minus 1 dPr by PR. These are expressions for HR by RTC and SR by R. Let us concentrate on these two. These two equations can be written in terms of Z0 and Z1 by using the eccentric factor. The earlier expressions were only in terms of Z, and we could write those expressions in terms of some terms containing Z0 and the other terms containing Z1 if we substitute the Z there as Z0 plus omega times Z1. Okay. What I would like you to do is substitute Z equals Z0 plus omega times Z1 in the previous equations 348 and 349 and group the terms appropriately in the integrals and get at the actual expressions. It is good for you to do that because I am not going to give the complete derivation here. It is good for you to do that and convince yourself that whatever I am going to present next is what you are actually getting. That improves confidence significantly. So take about 15 minutes, even if you are if you will take your time in doing that, please take about 15 minutes and then we will come back. 15 minutes please. Let us continue. If we do that, that is substitute z in the previous expressions in terms of z0 plus omega times z1, hr by RTC can be written as hr0 by RTC plus omega hr1 by RTC. I hope you would have already gotten some integral and so on and so forth which can be written in terms of hr0. You have an expression for hr by RTC earlier. So, a similar expression would have resulted for hr0 and a similar expression for hr1. Therefore, you could combine them both with the eccentric factor when the z was replaced with z0 plus omega times z1. So, hopefully you would have gotten this. If not, you can go back and check and see how to get this. We will call this equation 350, and SR by R can be grouped into SR0 by R plus omega times SR1 by R. We will call this equation 351. Why did we go through all this trouble of something that was of converting something that was given in terms of z to something in terms of a certain z0 and a certain z1, and therefore in terms of a certain hr0 and hr1 or sr0 and sr1 would become apparent now. We essentially did this because the quantities on the right hand side, something in terms of hr0 by RTC and hr1 by RTC and so on, these values are actually available to us. So, in order to use these values, we have formulated something for our quantities in terms of the available values. These were determined by Lee and Kessler. These are available as tables. In fact, these are available as tables in the appendix E5 to E12 in your textbook of Smith, Van Ness and Abbott. What I would like you to do now is not to take this on face value. Please take up your textbook, go to tables E5 and E12 and just get a feel, see what is listed there, what are the functions that are listed there, what are the kinds of values that are listed there from tables E5 to E12. I will give you about 5 minutes to do that. Essentially, we are getting familiar with the tables E5 to E12. Go ahead please, 5 minutes. Okay, let us continue. You have seen how the tables for HR0 by RTC, HR1 by RTC and SR0 by R and SR1 by R look like, and how you could use those tables at a particular situation when you know the values of the functions of which determine the values of the quantities HR0, HR1 and so on and so forth. The values of omega, as we have already seen, are available in table B1 in the appendix B of your textbook. We have already seen this, we do not have to go back and see it now. Just to recall, omega is one of the values that is given in the table along with many other constants for those pure substances. Therefore, the values of the residual properties HR and SR can be determined even without the need for the actual PVT data for each pure substance separately. So, that is the power of writing something in terms of residual properties and getting and using the generalized correlations that result from the generalized properties or residual properties. And we started concentrating on HR and SR, or HR by RTC and SR by R. From that you could get HR and SR, and from HR and SR we know that G or GR, G to begin with is defined as H minus TS, and therefore GR is defined as HR minus TSR. Once we have these values, we can substitute these here to also get the value of GR. And once the ideal values are known, we have already seen how to get the ideal values in terms of PVT and so on. The actual values of enthalpy and entropy can be estimated from the definition of the residual property. Residual property was actual minus the ideal, and therefore the actual is residual plus the ideal property, ideal gas property. To get a little more familiar with the use of generalized correlations, let us work out the example 3.4 here. We are going to continue with our favorite model system, isopropanol. The question here is estimate the residual enthalpy and residual entropy for the isopropanol system with the same conditions as given in example 3.1. please go ahead and do it. It is a straightforward thing. So, I do not think I will give you many hints here. If at all you need, I can give you the hint right now and give you some extra time also. This is residual enthalpy and residual entropy. We have expressions for residual enthalpy and residual entropy in terms of HR0 and HR1, and you know where those HR0 and HR1 values can be found, tables E5 to E12 of your textbook. So, go ahead and do this. 15 minutes please. hopefully you would have found the values of residual entropy and residual enthalpy. Let me quickly show you the solution, you can check whether you got the same. Our TC PC values are known, 508.3 Kelvin and 47.62 bar, and therefore for the conditions of temperature and pressure in the problem, which is 200 degrees C and 10 atmospheres if I remember correctly, the residual temperature will turn out to be 0.931. This is 200 degrees C plus 273, so 473 Kelvin divided by the TC value 508.3, that turns out to be 0.931, and our PR residual pressure is 10 atmospheres divided by PC 47.62, and that will turn out to be 0.21. Going to the tables in the appendices of the textbook, the value of HR 0 by RTC will be minus 0.246 from table E5, and the value of HR 1 by RTC would turn out to be 0.265 minus 0.265 from table E6. Omega, as we all know, we have already seen earlier, was 0.665 from I think table B1, yeah, table B1 of the textbook appendix, and therefore from our equation 343 that we had seen earlier, it will come back to you, we do not have to go back. HR by RTC is minus 0.246 plus omega 0.665 into minus 0.265, which will turn out to be minus 0.422, and HR and therefore HR is minus 0.422 into R into TC, which will turn out to be minus 0.422 into 8.31 into 508.3, that is minus 1782.52 joules per mole. Now we have the HR value here. We still need to worry about SR, that can be obtained again from the values given in the tables. SR 0 by R from will turn out to be minus 0.179 from the value given in table E9 of your textbook, and SR 1 by R is minus 0.254 from the table E10 of your textbook, and therefore from equation 344 SR by R is SR naught by R plus omega times SR 1 by R, which will turn out to be minus 0.348. Therefore, the SR value is minus 0.348 into R, which is 8.31, and that is minus 2.892 joules per mole per Kelvin. So, that is what we were expected to find. Let us stop here today, and in the next class we will start with the estimation of the fugacity coefficient.